Hello and welcome to the Machine Learning Podcast, the podcast about going from idea to delivery with machine learning. Your host is Tobias Macey, and today I'm interviewing Molham Aref about relational AI and the principles behind it for powering intelligent applications. So, Molham, can you start by introducing yourself?
Hi, Tobias. Thanks for having me. I'm Molham. I'm CEO and founder of RelationalAI. We are building an extension to platforms and systems like Snowflake that allows them to support AI-style workloads that they don't normally support. I live in California, and I'm an engineer by education. I've been doing AI and machine learning related things under different names for a little over 30 years now, going back to the early 90s when I worked on a earlier generation of neural networks.
Yeah, it's definitely interesting the shifts that we've gone through in our phrasing around these things when the base elements are the same. I remember when I first started hearing about this, it was all about data mining, and then it became, machine learning, and now everybody just talks about AI, which is the output of the machine learning, but we just want to ignore that part of it.
Yeah, the company I worked for in the early 90s had a trademark on the term database mining. And so people sort of evolved to using the term data mining. So it's funny that you bring that up. And back then, AI had such a negative connotation because we had come out of an AI winter that some people called it computational intelligence, not artificial intelligence. So,
And do you remember how you first got started working in machine learning?
yeah, I mean, I've always been interested in teaching computers to do things that approximated some aspect of what I do or what people do. So it's an interest from an early age. But I remember taking a course in graduate school at Georgia Tech that was about neural networks. And I also took lots of classes in signal processing. So that was sort of an early exposure. And then I got a summer internship with AT&T working on computer vision systems. And I was hooked. At the end of the summer, they offered me a full-time job, and I sort of gave up my academic aspirations and joined to work on computer vision systems in the early 90s. This is long before deep learning, and this is when you were still doing feature engineering by hand and all that stuff. But yeah, it was too much fun not to do full-time.
And now bringing us up to what you're building today with relational AI, can you give a bit of an overview about what that is and some of the story behind how it came to be and why this is where you want to spend your time and energy?
Yeah, so my interest in the area started with the models. How do you teach a computer how to recognize something or see something, or how do you predict something before it happens, and so on. But it becomes pretty obvious pretty quickly that the model and the model building is actually a small part of the overall solution that you have to build to deploy that model. So, for example, I worked for a company called HNC Software in the early and mid 90s, and they had sort of, I think they were one of the first companies to make money off neural networks by using them to build credit card fraud detection solutions. Okay. And so the model, of course, that predicted whether a transaction was fraud or not was a very important component, but there was so much more to it. It's a lot of data management that has to happen in order for you to curate the data that shows you examples of fraudulent and non-fraudulent credit card transactions. There's a lot of infrastructure you have to put in place to score the transaction and do it real time. The way you build a model has to accommodate the scoring criteria, right? Because you can't afford to process a terabyte of data when you score, a million credit card transactions an hour or something like that, right? So once you get a score, what you do with that score plugs into some workflow that the credit card issuer has to, has to feel good about and supports their business strategy. So he quickly realized that you have to combine a variety of technologies together to put together an intelligent application, transactional data management technology, analytical data management technology, planning technology. You have to combine programming languages and capture business logic and workflow and all this stuff. And it was really, on some level, awful, soul-crushing work to do all of that stuff. And I've spent the last 30 years thinking about how to simplify that and how to make it so much easier to go from model creation to deploying it in real world context. So,
And then also, when I was going through your site and getting ready for this interview, one of the phrases that jumped out at me is this idea of the AI coprocessor. And you mentioned that relational AI is designed to work in conjunction with something like Snowflake. But I'm wondering if you can just unpack that phrase for me a bit and explain what it is that you're trying to convey with that terminology.
Yeah, so it's obviously you know an analogy to coprocessors, like hardware coprocessors that live on the motherboard of your device, for example. Back in the 80s, you used to have coprocessors for doing floating point arithmetic, for example. Today, you have GPUs that sit on the same motherboard as the CPU, and the CPU can offload certain computations to the GPU because it's much more effective at doing them. So if you want to do graphics or gaming, or if you want to do machine learning or anything like that, you can do it on a CPU. It's just much more expensive, much slower. So what we're doing here is, by analogy, we have a database coprocessor. It's a software coprocessor to database platforms and data clouds like Snowflake, where we help them do things that they're not designed to do. So, for example, prescriptive analytics, working with solvers like linear programming, integer programming solvers, or simulation, or certain types of machine learning, or graph analytics, or rule-based reasoning. So a combination of techniques that are symbolic and probabilistic and statistical that we know we have to use to build real world enterprise applications. Snowflake doesn't do those things, and they will tell you that they don't do those things. And the alternative to working with a solution like ours is to copy data out of Snowflake, put it in a point solution that does the graphs, or that does the prescriptive analytics or the predictive analytics, have it operate there, and then you bring the results back in. That's problematic and in a lot of ways, and that kind of glue that you have to use to do that is what creates the soul crushing work that I told you about earlier. So a coprocessor is embedded in Snowflake. It runs inside the security perimeter. It respects the same governance machinery that you have in place, and it eliminates the need for manual data synchronization because the data structures are automatically synchronized with the data in Snowflake. So we organize data in the form of a knowledge graph as a set of materialized views on the tables in Snowflake. The other criteria for being a coprocessor is it's cloud native, architected in the same way as Snowflake, separating storage from compute, which means you get time travel and versioning, zero copy cloning, workload isolation. You get consumption pricing, which is very important for people who use the cloud computing, and systems like Snowflake. And then the third criteria for being a coprocessor is that we implement the same paradigm, meaning Snowflake organizes things using the relational paradigm, and we're a coprocessor that lets you support these workloads I mentioned also relationally. So you don't have this impedance mismatch, and you have to translate data structured in the form of relations and tables into navigational graphs or tensors or some procedural abstraction and so on. So by being embedded, by being cloud native, by being relational, it just eliminates so much friction from deploying AI and building intelligence into applications and building intelligent applications in general. So
That's another interesting phrase to unpack that gets used in various contexts is the idea of an intelligent application, where to some measure software in general is intelligence because it is being embedded with the business rules that are painstakingly encoded by the software engineers. But typically that idea of intelligent applications implies some level of autonomy and self-learning. I'm curious if you can give some color as to how you think about the situations in which that phrase is applicable, and what are some of the ways that maybe you've seen it misapplied.
yeah, so it's really interesting that you make the connection here, Tobias, to the fact that application logic is in some sense codifying some domain knowledge, background knowledge that's usually in the head of a business person or a developer, right? So that is very sort of like a classic symbolic representation of knowledge and expertise. Now you can do that. You can represent that procedurally, as is the norm these days. Your application logic is written usually in a Java or C# or COBOL or some procedural language like that. But you can also represent it declaratively. Okay, and so SQL is in a sense a step in that in that direction, because you basically can ask a question without necessarily telling the computer how to answer that question. It sort of figures out an execution strategy for answering the question. It optimizes it. It parallelizes it. It takes care of out of core memory concerns and all of that kind of stuff. So, but there are many more ways of representing knowledge. You can represent knowledge statistically. You can represent knowledge in the form of parameters to a neural network. Okay, so it's sort of a way of taking lots and lots of examples of some phenomena you're studying, and then compressing them into a much smaller data set that's the parameters of the model. Even these very large language models, I think one of the abstractions that you keep reading about is that they're really compressing the data that they've been trained with. Okay, and so that compression is a way of abstracting over detail and capturing the essence, some fundamental aspect of the underlying phenomena. So yeah, in that sense, you can argue that all applications have some form of either symbolic or statistical intelligence. But really what I'm talking about, and I think what the world means when they talk about intelligent applications, are applications that are helping you predict some outcome, helping you see into the future a little bit, and knowing, for example, that something is likely to be fraudulent, or knowing that some user is likely to prefer a certain product, or knowing how much someone will pay for something, and then take action, using maybe even prescriptive intelligence, prescriptive analytics, take action to maximize the value to that person and to the business serving the person. Okay, so usually or historically, at least, many types of apps like ERP apps and HCM apps and so on, they're just sort of getting input from a human, and the human has to predict and decide what sort of the best course of action is here. But when you can make the application sort of help you with a decision by giving you plausible predictions and giving you plausible recommendations as what to do about them, then that makes the application more intelligent, because it's taking on some of that cognitive burden that you would have as a user otherwise. So.
And for people who are employing relational AI in their business contexts, what are some of the primary use cases that you're focused on solving for them, and the reasons that they would turn to relational AI in place of or in addition to other solutions that they may already be using?
Yeah. So yeah, thank you for that question. So again, if you're not using something, your relational AI or something like relational AI, you're typically having to resort to stitching together a lot of point solutions that specialize in these various workloads that you need to put together to build intelligence into an application. So specifically, again, graph analytics, rule-based reasoning, prescriptive analytics like integer programming, linear programming, simulation and probabilistic programming, machine learning methods in a variety of flavors, and language models. Okay. And so we have clients, for example, that use graph analytics to build more sophisticated features that they can feed into fraud models and improve the predictive accuracy of those fraud models, saving them hundreds of millions of dollars. Okay. We have clients that are capturing semantics that go with their data. They're moving all their data from thousands of databases that support thousands and tens of thousands of applications. They're moving it into platforms like Snowflake, but they can't move the business logic, because the business logic is not relational in SQL, and so they use us to capture the semantics declaratively, so that they can understand the relationships between various data silos and navigate these data silos in ways that they wouldn't otherwise be able to navigate, again uncovering hundreds of millions of dollars of value in the process. We have clients that are replacing legacy applications that were developed in the traditional way that you described, hundreds of thousands of lines procedural code, and representing that background knowledge declaratively, and then reasoning over that knowledge in a way that reduces the amount of code by a factor of 30, 40, 50, making it more accessible to business users, making it more scalable, making it higher quality and more adaptable, and so on. We have clients that are starting to combine what we do with knowledge graphs and language models to help language models answer questions more accurately and more effectively. So You might have seen folks, for example, that use a language model, ask it a question, and then generate a SQL query that can run on data living in a SQL database like Snowflake. Well, if the data models are really trivial and the question is really simple, usually you don't need to help the language model that much. It can usually kind of give you the SQL query that gives you the answer. However, as the questions get more complicated or the data models get more complicated in the real world, we see customers with hundreds of millions of columns of information in Snowflake. The language model needs something like a semantic layer or a knowledge graph to help it navigate the data. And it also needs the ability, like if you're going to ask a question that helps you identify groups of or clicks of connected customers in your database, well, that's a graph query. That's not a query that a SQL database can answer very easily. Or if you wanted to ask a question that says, find me the shortest path from point A to point B, that might require some kind of reasoning capability or solver capability. Or if you're asking a question like, what will my sales be of Coca-Cola product in the Northeast next week? Well, that data doesn't live in Snowflake. You have to sort of infer it from the data that lives in Snowflake using maybe graph neural networks or other technologies to complete the database with information that it lacks, and that again can't be answered in straightforward SQL queries. So there's just so many different applications of this technology across the board for improving existing models, for creating new types of models, for replacing very complex, fragile code that tries to glue a bunch of things together, for augmenting the power of language models. I can keep going. I might have taken too much time with my answer, but there's just so many different ways you can use this.
For people who aren't using relational AI, you mentioned some of the types of systems that they might lean to, having to cobble them all together. What are the, I guess, orders of magnitude of ease of use or maybe efficiency improvements that they might expect by moving to relational AI? And are they able to just completely obviate whole classes of their infrastructure? Or is this a situation where those other components still serve a role, but they are not in the critical path as much as they would be otherwise?
I think mostly obviate. So if you have, again, I use Snowflake because that's the platform that we launched around last June, and they created this category of a data cloud, and they I think lead that category. We do see other systems like BigQuery, for example, in the Fortune 500 and in big companies, but generally Snowflake is sort of the most popular platform. Yeah, so if you have Snowflake and you use us as a coprocessor for the workloads it doesn't support, that you're just not having to deal with whole classes of systems. You don't need to copy the data out and put it in navigational graph technology if you want to want to improve feature engineering with graphs. You don't need a totally separate rule based system to build dynamic applications that have evolving ontology and evolving business logic. You don't need a whole separate stack for integrating Gurobi or Cplex or a variety of other integer programming, linear programming solvers. I keep coming back to these because we don't often talk about them in the context of machine learning anymore, but this is like one of the original magical technologies that made it possible to do things that you could have classified as AI, and we should still probably classify as sort of important to AI. In fact, all machine learning is built on optimization, mathematical optimization, right? Usually with the gradient descent type techniques, and so optimization is a very fundamental building block for intelligence. And so our supply chain networks, like the world runs using this kind of technology, like no truck or airplane or train or ship goes from point A to point B usually without being scheduled using these kinds of techniques. Today, there's just a totally different stack that you use for that lives outside of your primary data management platforms. What happens if it lives inside? Okay, same for simulation. So I'm not saying that overnight people will have turned all that stuff off and use us in Snowflake. I'm saying you can avoid compounding the hairball that you have now by starting to do new work this way, and then over time refactor the old stuff, the legacy stuff, so that it's running in a more streamlined fashion. Okay, but certainly the more point solutions you rely on, the the more energy you spend on glue between the point solutions than actually creating business value. And we want to eliminate the glue.
So, in terms of the actual platform that you're building, can you talk through what the system architecture looks like, some of the ways that you think about the technological underpinnings of the problem, and how you've approached that architectural design element?
Yeah. So again, thank you for that question. So one of the really interesting things about what we do is we do all of this stuff in a relational context, right? And so in my experience, being maybe slightly older than most of your audience here, if you observe, you step back and you look at our industry over the last 40, 50 years, going back to, the 70s when the relational model was first introduced, usually the relational model is not taken very seriously for the important workload of the day. So in the 70s and 80s, it was transactional systems, OLTP, and real engineers built transactional systems using navigational database technology, and they wrote COBOL and they followed pointers around to do transaction processing. And the relational model was dismissed on a variety of ways, including, hey, it's never going to perform, it's too slow, and also including that real engineers don't want to understand relations, and they want to write programs, they want to write code. Okay. And then of course the database community invents join algorithms, data structures like B trees, techniques for dealing with ACID properties and concurrency and so on, languages like SQL, and seemingly overnight, the world switches from using navigational database technology to relational technology for building transactional systems. Okay, and companies like Oracle are created with other players in the area that basically no one thinks about building OLTP systems now, like a checking system, like taking $10 out of checking, put it in savings. Like you'd be nuts to try to do that in a different kind of technology. So in the 90s, the same kind of phenomena, analytics, being able to do descriptive analytics, lots of aggregations and lots of BI type stuff. It was deemed like certifiably nutty to try to do that in a relational database, because the right answer was clearly multidimensional arrays, or what we would call tensors, because that's how you get high performance and that's how you do things. And don't waste our time with the SQL relational stuff. And the community invented column stores, bitmap indices, vectorized query processing, and all of that stuff. It's the beauty of the relational models. You can separate the abstraction from how you do the work. And we went from debating, MOLAP, multidimensional OLAP versus ROLAP, to basically the only OLAP you get today is relational. Like even if you Google MOLAP now, you don't get that many hits anymore. It's sort of been erased from the collective memory. The third sort of version or example of this is 10, 15 years ago, big data was the new workload. Relational models dead. Stuff is not going to work. MapReduce and Hadoop is the answer. There were three big Hadoop companies, Cloudera and MapR and Hortonworks, and dozens, maybe hundreds of companies built, and funded to build analytics on top of Hadoop, because that's the way you do big data, and that's the only way you can do big data. There was one exception to that, one company, little company called Snowflake, that in 2012 was saying, actually, the relational paradigm lets us pick a different architecture, a cloud native architecture where you separate storage and compute, and we can actually do big data without all the complexity of Hadoop and without all the procedural stuff that that we have to worry about. And the CEO of Snowflake from 2014 to 2019 is Bob Muglia, and Bob is a huge supporter of our company. He's a big investor and is on our board and is very active in our company. He told me that 2 or 3 years before Snowflake had the most successful IPO of all time, he was turned down for funding. I don't remember, 24 times, 27 times, like some stupid number of times, because people just like Hadoop. They knew Hadoop was the answer, or like why would Snowflake be successful in a world that has Teradata and so on. So very long-winded setup to answer your question. So our machinery is fundamentally relational. Okay, so we have a relational system. We organize data in the form of relations. They're a very normalized, using very normalized data structures or schemas. So we call it graph normal form. And normally, with normal relational machinery built for OLTP or OLAP or big data, they wouldn't be able to support working on highly normalized data, and they wouldn't be able to support running queries that have lots of self joins, which are important for, say, graph analytics, or queries that are based on recursion. which are also important for reasoning and other things. But my colleagues have invented a new classes of join algorithms called worst case optimal join algorithms that make it efficient to join together 10, 20, 30 relations. We've invented new classes of query optimization called semantic query optimization that uses background knowledge about the domain that you have to actually make queries run faster by avoiding having to consider certain options. We've done that in a cloud native architecture. We've done that using and relying on very sophisticated incremental view maintenance algorithms so that if you change a record in a Snowflake table, you can update the materialized views that depend on that. Our knowledge graph that depends on that updated efficiently, which is very important to be able to do a lot of things in spreadsheety style way. We've invented relational language features that make it possible to efficiently and easily express these non-trivial things that are either impossible or unwieldy to express in SQL. And we've done other types of engineering to make it so that we have a relational database engine with these new data structures and architecture and joint algorithms and so on that can just natively answer a graph query in a way that a classic system cannot. So, it's really pretty basic. It's like these 5 or 6 innovations that you can combine together in various ways to get that expressive power and that support for those workloads that we just discussed. Okay, so it's not what people expect in a sense, because they've been conditioned to learn that if you want to do graph queries, you need navigational technology. Just like in the 70s, it was like if you want to do OLTP, you need to follow pointers around and so on. So there's some real deep, science here and deep engineering that pulled together extends the power of the relational paradigm to these workloads that historically it hasn't handled. So.
And as a brief side note to the history of the Hadoop wave, also, is that by the time everybody else was starting to use Hadoop, Google, who kicked off that whole trend, had already moved past it and said, this actually
Yes,
doesn't work. We're going to go on to Bigtable instead.
it's too hard. They started building SQL systems, and even the Hadoop community, it was like a little laughable. Like it was like at first a very anti-SQL, and then they realized, actually this stuff really is simplifies away a lot of complexity, and they all started building layers that made them look more and more like relational databases. But they had this sort of very
Mm-hmm.
complex on-premise architecture underneath. And like to me today, when you talk to most people, Hadoop is kind of in the same equivalence class as COBOL.
Right.
It's just old legacy stuff that we have to run because we can't afford to migrate it. But also, lots of people are now, like in the context of the sort of our customers and so on, the engineers we work with and the executives we work with their bonuses are being attached to migrating off legacy Hadoop systems in on-premise non-cloud native systems to Snowflake and BigQuery and systems like that. And so there's still a lot more going that way. And I think those companies and those products are very well positioned in this world as people migrate away from these very complex, very expensive systems.
Another interesting side note is the discussion around this relational paradigm, this relational model. My understanding also of some of the historical context there is that this idea of relational algebra is what kicked off the implementation of SQL and this whole wave of databases, but that SQL was only ever a subset of the actual relational algebra that was proposed, and also that graph systems are actually better for expressing relationships as opposed to the
Exactly.
relational approach of SQL. I'm wondering if you can talk to
Yes.
some of the ways that that dichotomy manifests in your work with relational AI, of maybe being able to extend the relational algebra beyond what is expressible in SQL.
Yeah, exactly. We extended the relational algebra with two things, okay, like a multi-way join operator. So like in the relational algebra as defined by COD, the operators were either unary or binary, okay? And stop me if this is more detailed than you want, okay? So they either operate on one relation or two relations at a time. So if you're joining together 10 things, you would pick any two of them, join them together, and then you produce a temporary, and then you would then join to the third, produce a temporary, join to the fourth, right? So the amount of work you have to do is proportional to the size of that biggest temporary. Okay, so so binary joins are fundamentally limited this way. Okay, now when you introduce multi-way joins, worst case optimal joins, you're joining all 10 things simultaneously. Okay, so if you want to like join 10 things to count at paths of length 10, with binary joins you have to count all the paths of length 2. There are a lot of those. Then count all the paths of length 3. There are a lot of those, and keep going until you find just a few paths of length 10. Okay, so you do a lot of work that you end up throwing away because you're not interested in paths of length 2 and 3 and 4. Okay, with a worst case optimal join and with a semantic optimization, you just do work proportional to the paths of length 10, and you avoid doing all that work. So it's asymptotically faster in the same way that quicksort or merge sort is asymptotically faster than bubble sort. Okay, so that's the best way to get speed is not to have to do work. If you have to do the work, obviously you want to parallelize, you want to accelerate with GPUs, and you want to in memory and all that kind of stuff. But the best way is just to avoid doing the work altogether. Okay, and so by extending the relational algebra with this multi-way worst case optimal join operator and with a fixed point operator that lets it do recursion, you make it more expressive. Because one of the knocks on relational algebra and the relational calculus is that they didn't capture all the algorithms. Like they don't capture all polynomial time algorithms. Okay, and you have to add something like a fixed point operator or recursion to get basically to simulate while loops, okay, to make it so that it's expressive enough to capture polynomial time algorithms. Okay, so that's really the fundamental innovation. Is we've taken sort of Ted Codd's dreams and said, okay, well, he couldn't go all the way. We couldn't make it end to end relational because it wasn't expressive enough. It wasn't powerful enough. And it wasn't possible to do like certain things in an asymptotically optimal way. But you add these two operators and you add semantic optimization, and all of a sudden you can express a lot more, and you can just take care of programming in a much more general way. So you can take all that procedural code that we write as application logic and now formulate it relationally. And for the first time, you can define the whole application end to end relationally. Like deep learning was a big breakthrough because it defined the model end to end differentiably. Okay, and so you didn't have to do the symbolic feature engineering up front and then learn the parameters in the second stage. You're basically, each layer of a deep network sort of learns higher and higher abstractions and learns how to represent sort of the underlying features and so on. Well, there's a symbolic version of that, okay, which is sort of end-to-end relational definition of your whole application. And once you do that, you avoid the split brain architecture. You can now optimize across the whole thing, okay, and 10 to 100x times less work. In the same way that deep learning eliminated a whole bunch of feature engineering manual work, this kind of approach eliminates a whole bunch of programming work. Okay, at least in the same way by analogy, let's say. So yeah, it's very it's good it's interesting to see it from the perspective of first principles like that. Okay, not everybody will understand what it is just said, but there's a really deep contribution here to the foundations of the relational model. And the relational model, to me, is a superset of other models. Like, people will represent graphs with adjacency lists and pointers. That's one representation. People will represent graphs with tensors or matrices, having a matrix where if you have a 1 in a cell, that sort of implies a connection between two nodes. The relational abstraction, I think, is really the nicest abstraction way of representing graphs, because as you said, we often talk about graphs as defining relationships between two nodes. And so relation is the ideal abstraction, I think. And what's also really nice about the relation is you can now connect 3 nodes or 4 nodes. You can model hypergraphs and hyperedges. Okay, it generalizes very nicely beyond, much more nicely than, say, a matrix representation or especially a pointer-based or adjacency list representation. So it really is the right abstraction. And because it lets you separate the abstraction from the implementation, you can implement it with pointers or implement it with whatever you want to, whatever data structures work best, but the abstraction hides all that from you, and you can operate more productively as a result.
And so, for teams that are applying the relational AI platform to their problem domain, what does that onboarding and workflow look like from saying, okay, we are going to implement relational AI. Now I need to solve a problem where I need to generate some AI model to reduce the time to delivery, bringing the supply chain example to bear.
Yeah, yeah. This is something we do in practice today. And I just make sure your audience understands where we announced private preview of relational AI in June at the Snowflake Summit. Okay, and I expect that we'll be in public preview, sometime early next year, and GA certainly by next summit. Okay, so unfortunately, this is not something where your audience can just immediately go to our website and start working with it. We'll have to find a you have to get in touch with us, and we'll get you on the list, and we'll try to engage with you that way. But the way in principle it works is, if you're working in Snowflake, we meet you where you are. The first step is to create mappings from either accept default mappings or create your own mappings from the tables that you have in Snowflake to a graph normal form representation, which is what we call a relational knowledge graph, is just a graph normal form relational database. And this representation in graph normal form is going to be implemented as a set of materialized views. So in Snowflake, you might be used to idea of having different types of tables, like you have the base tables, you have dynamic tables, which are materialized views of a different kind. You have tables that you use for transactions. I think Unistore, I forget exactly what term they use. And so this is just a different kind of table that lets you represent the knowledge graph. And when you have a need for doing, something like the workloads I described, you can either via SQL interface interact with the knowledge graph and get answers to graph queries, for example, like PageRank or whatever your graph query or weakly connected components or whatever your graph query is. Those can be packaged up and just sort of taken care of automatically. Or you can, instead of calling into a stored procedural language, you would call into a stored relational language called rel that lets you express more or more easily what you couldn't express in SQL to capture, for example, the properties of an integer programming model. Now, what is an integer programming model or linear programming model? It's usually a set of constraints and an objective function. Well, databases have integrity constraints. They have views, and so the set of constraints are just relational integrity constraints. The mapping is almost one-to-one. And the objective function is just a view you define that says, here's how I think about cost or risk or profit, some objective that you're trying to minimize or maximize. And then you tell the system, find me a relation, find me a table that you automatically populate with the price points that are going to maximize my profit. Okay. It's a very, very natural extension, like the correspondence between how you think about problems in an integer programming, linear programming sense, and how you think about building models in a relational sense. It's like, again, you don't have to squint very hard and see the same thing. So again, graph queries are relational queries with self joins and recursion. You don't have to squint very hard to see the correspondence. A graph is a binary relation. A hypergraph is an n-ary relation, depending on the edges. Tensors are relations that map integers to a value, right? Like you think about like a three-dimensional matrix or a tensor, you have IJK as the columns that are in the key that map to a value. Now, tensors can be dense or sparse. In the relational database, that's all abstracted away from you, and the internal representation can compress away zeros if you're sparse, for example. That's that's sort of the default setting in a relational database, is to assume your data is sparse. And if your data is dense, you can then imagine putting data structures behind that will compress away the IJK, because you don't need to store the indices when you're dealing with dense data. Okay, so again, I don't know if this all made sense, but it's a very, very natural correspondence between the tensor world and the relational world. Linear algebra and relational algebra. I think relational algebra is a superset, and relations are a superset of tensors. Same for graphs. Same for things like linear programming and integer programming and so on.
With that concept of being able to build up these tensors as a graph representation, it brings to mind the other set of technologies that are gaining a lot of attention right now of vector databases being used as a context embedding method for being able to feed to large language models. That's what everybody wants to talk about
Yep.
right now. And then there are systems like Pathway is another platform that is built as a streaming engine where they are focused on being able to build end-to-end LLM applications without having a vector store. I'm wondering what are some of the ways that the system that you're building at Relational AI maps into the broader context of ML ops, where you're thinking about things like feature stores, vector stores, model training, model serving, just some of the ways that for ML teams who are trying to reduce the surface area of systems and problem areas that they need to be able to focus on to get their job done. What are the ways that they will be leaning on relational AI to get to where they want to be?
Yeah, so a lot I can say here. Let me say a couple of things. So first of all, systems like Pinecone and other vector databases are very specialized technology to do basically nearest neighbor queries against these embeddings, these vectors. Okay, so and because they have like just one problem to solve, they can really focus on it, and they tend to solve it really well. And there are many different approaches or systems out there that people can pick from. So, but at their core, there's a query. Who are the nearest neighbors to this vector? And at the core is a vector, which has a binary relation that maps an integer that is the index to a value, in that 512 row, if you will, or this vector size of 512 or 256 or 1024 or whatever sizes embeddings are these days. So it's just super super specialized to that. Now we're not in a position to be as specialized for this workload. Like you can do those types of computations in what we do, but they're not going to be as efficient or as scalable as, say, in a specialized technology, at least for the time being. So we typically will want to incorporate some kind of vector technology into the mix. For things like feature stores, though, there's a ton of value that we can add. So one of our clients implemented a feature store, and they discovered that, and they're very excited about it. And they discovered that lots of data scientists were putting lots of features in a feature store, but because there wasn't an easy way to navigate that feature store, there wasn't a knowledge graph or some kind of semantic representation of what's going on in these features. A data scientist will come into the feature store, do a keyword search or two, not find what they want, not even be sure they know, if they find something that sounds like what they want, they don't know how it's actually stitched together and so on. So they would just end up rolling their own feature anyways, and then putting it in the feature store. Okay. So it became, they called it, not my terminology, a feature swamp. And it just sort of accumulated more and more features. In the same way, other databases, we have customers with 180 million columns of information. Like we know banks that have over 400 million columns of information. You can't convince me that there isn't a ton of redundancy in 180 million columns of information. It's just different data silos developed by different people at different times, and they don't know that something has been developed before because they don't have semantics. They can't query based on semantics, not just in the vector embedding sense, semantics in like here's the computation, here's the definition of what this piece of information means. So building a knowledge graph on top of a feature store and taking each feature and being able to understand the ingredients of that feature, like what data elements went into it, and then the recipe, how do you combine those data elements, made it possible to avoid having data scientists give up quickly and roll their own feature, and made it possible to eliminate, obviously, a lot of redundant work, labor, but also computation. People don't love the monthly cloud bill that they get, but also storage, right? And again, reduce complexity in a way that you couldn't do if you didn't have a semantic layer or semantic understanding what's going on in your feature store. So, anyways, there's a couple comments on your question there. So.
Another aspect of what you're building that I'm curious about is the design philosophy of how to strike the right balance between I want to make this super easy for you to onboard and be able to do complex things like named entity recognition, do that convergence of I have, as you were saying, 400 million or however many millions of columns of data, maybe 20% of which are actually redundant. I want to be able to automatically help you find that and coalesce that into a single representation versus
Yeah.
here are all the primitives for you to be able to do that, and maybe here's a recipe book for some examples and just some of the ways that you think about that design philosophy and product philosophy of what you're really driving for.
Yeah, I mean, look, before language models, we just have to acknowledge that a lot of this is, fundamentally manual. Okay, you can help, here and there, but I think language models have really changed my thinking on that. It's still early days. We're only, I learned about language models last December. So what is that? 10 months, 11 months. But we've been doing a lot of work to try to sort of use language models to accelerate, like with a human in the loop still, okay, but accelerate knowledge graph creation and being able to map those 100 million columns or 200 million columns to a much simpler ontology with much simpler set of relationships. In some cases, being able to identify that, hey, this column is really just an aggregation of this other column, and it's not that hard. I can kind of figure it out from the data and from the naming convention. And so you can, start eliminating, if you have 100 million columns of stuff, you probably have 100,000 columns that are input data. Everything else is probably computed from that. So language models can accelerate the development of the ontology, the semantic layer, the knowledge graph, and even the development of capturing the semantics of how something is computed from other things. And the beautiful thing about that is once you have such an ontology, such a knowledge graph, that makes it as possible to use the language model to answer questions it couldn't answer because it's not grounded in truth and it doesn't know how to access 100 million columns on its own. So I do think there's a lot that's going to happen here in the next 2 or 3 years to give us a handle on this mess of data that most companies have. Like most companies have thousands of databases that drive many thousands of applications, all developed independently, all separating business logic in code from data and data model. The cloud and systems like Snowflake made it possible for the first time. They're so scalable, made it possible to put all that data in one place. And now this next step is to realign that data or to simplify that footprint into something that a human being can wrap their brain around. Because there's no way you can wrap your brain around 100 million things. So.
And in your work of helping customers onboard onto the platform, understand the capabilities that it offers, figure out how best to apply it to their problem domains, what are the elements of customer education that you find yourself spending the most time on, or some of the aspects of the platform that are maybe overlooked or underutilized that you want to bring to mind as people are trying to figure out how best to solve the problem given the tools that you're providing?
Yeah, look, it's early days for us, and building a system like us that sort of revisits data management fundamentals from first principles. It requires a lot of energy into algorithms and data structures and so on, and that energy has come at the expense of creating a more streamlined experience for users. Okay, so I would love to have more complete tooling, better tooling. I would love to basically take the feedback that we've gotten from sort of early adopters about the language and what subset of it is accessible and to make it just all much smoother than it is today. So it's smooth in the context of we meet you at Snowflake and we'll hopefully meet you in other places where people are over time, but there's still a lot to do to create a tooling and an education framework and to be able to build on people's comfort and understanding of the relational model so that what we do uh, doesn't seem so new and strange. Okay, so apologize in advance to some of the early users here who've helped us get that feedback that we need to create a more complete and more usable experience. So I think there's more work to do there. I think with the kind of platform that we build, again, combined with Snowflake and cloud computing, you can start bringing together modeling environments that normally you would have thought of, separate, like, modeling, you build models in your databases, but you also build models in your spreadsheets. These two modeling environments have been like really disconnected. With the technology that we're putting in place, you can imagine a more live modeling environment like you get in a spreadsheet where you're building the concepts and the relationships between the concepts, but you're also like doing that in an environment where there's data and it's running and you're getting instant feedback about how input changes affect outputs and all of that. So that's not a this year or next year thing, but that's a down the road thing for us that I'm excited to earn the right to get there at some point in the not too distant future. So
And recognizing that you are still relatively early in your journey, for the customers who are applying your engine for the problems that they are trying to solve, what are some of the most interesting or innovative or unexpected ways that you've seen it used?
Like the stuff with the language models has been really interesting. We just did something with a client who's working in supply chain management, where also they use our system to do simulation, which was also really interesting because you don't normally think about like writing a simulation in a relational technology. I was very surprised. We have a client that is building tax applications, and in one subset of that, like we replaced something like 100,000 lines of C# with about 7 pages of relational rules. It's not common. It's not like the default. Like usually you see 10x reduction, 20, 30x reduction, but that kind of compression was really interesting to see. We have internal hackathons and people have built like games and non-traditional applications using systems like this. So yeah, it's a pretty versatile model, and it'd be great to see what people do with it once it's in the hands of the masses. So.
And as you have been building this platform, building the business, what are the most interesting or unexpected or challenging lessons that you've learned in the process?
Look, it was one of the most challenging things. Like when you build a business, you're building the company, but you're also building a product, and then you're trying to build a market or a category that all fits in, right? And we've had sort of the confidence around our product and the value proposition of our product, but we didn't know how to explain it to people. We didn't know how to get people interested in what we do. Some of the what we talked about today in terms of the fundamentals and the foundation, like that's interesting to people with our background, but it's not interesting, to a bank or a retailer or whatever. And one of the best lessons I've learned is the importance of getting the go-to-market motion right, and really how to meet people where they are and articulate the value proposition in a way that they get excited about, which might be for totally different reasons that I'm excited about, and so this is real. I'm really happy with the response of the market to this positioning of us being a co-processor to Snowflake, because like who wants another database system, right? Like, but people who've made the big investment in a Snowflake or a BigQuery, they want that to do everything that they want. And so positioning our technology, not just, database number 857, but as a way of augmenting a platform that people are adopting, that people love, like the Snowflake Net Promoter Score is like 70 plus. Okay. I mean, that's a good solution, a good technology that people really appreciate. And then plugging into that in a way that people really just obviously understand that there's a whole bunch of pain they don't have to deal with anymore, okay, and a whole bunch of risk around security and so on, and a whole bunch of processes like budgeting they don't have to deal with anymore. All right, so as a technologist, I hate to answer the question, like in a sense of like my best lesson is the business side, is a business lesson and a go-to-market lesson, because as a technologist, we all want to have impact, and you can't have impact if you don't have a way of getting to users and buyers and so on. So,
And for people who are interested in what you're building at Relational AI, what are the cases where it's the wrong choice?
look, if you want something on premise, we're the wrong choice. If you want something like, if you're the kind of buyer that wants something like super polished, okay, we're not yet the right choice. Okay, we are earlier in our journey. Just depending, like people have just sort of different philosophies around where they want to be in the adoption curve. So we are newer, more innovative, more different, and so you have to factor that in. There will be issues related to that, but again, if it's, let's say it's 2017 and you're trying to make a decision between a Hadoop based thing or a Snowflake based thing, right? In hindsight, what would you do knowing where we are today? Hadoop was more mature, it had lots more users, it had more proof points than Snowflake. And so you could argue that in 2017 Hadoop was the right choice, but you can also argue that knowing that by 2020 Hadoop was the wrong choice, do you want to pay that early adopter tax, so that you invest in a technology that's going to be with you for the next decade or two, versus a technology that's about to become obsolete? So that's the trade-off.
And as you continue to build and iterate on the product and the business for relational AI, what are some of the things you have planned for the near to medium term, or any of the problem areas or projects that you're excited to dig into?
Yeah. So again, get to GA on Snowpark Container Services, which is Snowflake. That's a priority. Make the system just more polished and more easy to just get going with. Reduce some of the complexity around sort of modeling and so on. There is a workload that I would love to get to that we were working on in the lab, but not in production yet, which is around using graph neural networks to answer questions about data, that you don't have, like the example I used earlier about like, what will my sales be next week, right? It's a graph completion problem, right? And so I would love to have like a deep learning technology for structured data. It doesn't really exist yet. We have it for images and we have it for text, and we've eliminated feature engineering, for those types of problems, but we haven't really eliminated feature engineering for enterprise data yet. Yeah. And so, graph neural networks might be a path towards that. And so you're using, what you have in your database to predict and the things that you don't have in your database, like things that are in the future, for example, or things that you can't measure. So yeah, there's a ton of cool work that we'll be doing in the years to come. So
Are there any other aspects of the work that you're doing at Relational AI, the problem space that you're addressing, the business, or just the kind of white spaces in the market that we didn't discuss yet that you'd like to cover before we close out the show?
no, I think this is pretty comprehensive. So thank you, Tobias. Thank you for all the great questions.
Well, for anybody who wants to get in touch with you and follow along with the work that you and your team are doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest barrier to adoption for machine learning today.
Well, it's clearly, I mean, I would be inconsistent if I don't say the complexity of pulling it all together, right? Just too many moving parts, too many paradigms, too many. Just it's mundane, it's tedious, but it's overwhelming. So that's, I think, a big one. And then in the enterprise space, having to do manual feature engineering is a bear. It makes models very expensive to build, and so you don't get to build as many models and deploy in as many decision making cycles and loops and so on.
Well, thank you very much for taking the time today to join me and share the work that you are doing on relational AI. It's definitely a very interesting product, interesting problem domain. It's great to see somebody tackling this space and making this kind of discovery of data and building of intelligent applications a more tractable problem without having to deploy as many moving parts. So I appreciate the time and energy that you folks are putting into that, and I hope you enjoy the rest of your day.
Thanks, Tobias. Hopefully, we'll talk again soon. Thank you.
Thank you for listening, and don't forget to check out our other shows, the Data Engineering Podcast, which covers the latest in modern data management, and Podcasts.init, which covers the Python language, its community, and the innovative ways it is being used. You can visit the site at themachinelearningpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at themachinelearningpodcast.com with your story. To help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.